So good morning, good afternoon, and good evening, everybody. And today we are here to introduce you with our third release of MSC Apex, which is MSC Apex Cheetah. Prior to this, about a year ago, we have released the first version of MSC Apex, which was Arctic Wolf, that was exclusively targeted for modeling, and that was empowered with the direct modeling and meshing engines built in. After we got the feedback from you folks, then we made the second release, which is Black Marlin, which was also targeted for the modeler only with additional features that you guys have requested. Today here we are introducing MSC Apex Cheetah third release. Unlike the other two, this release comes with two product lines. One is MSC Apex Cheetah Structures, and the second one, continued enhancements on the modeler. The structures, this is a new paradigm of simulation and built all new with what we call computational parts based assembly architecture, and it also comes with the generative behavior. And this is the first release of structures product line in MSC Apex. On the modeler side, we continue to enhance the functionalities for the modeling, and at this time we have focused on providing you the tools that helps you to do the mid-surface modeling for the most complex 3D geometries. The structures, as I said, comes up with the strong foundation that includes what is the integrated solver, the first of a kind in the industry, and it comes with what is called computational parts assembly architecture. I will talk about that in a minute. And it has the generative behavior, and the product is, the technology is incremental solver. Because of the computational parts based system, we should be able to incrementally solve any component in an assembly. And the assembly of the parts in the system is supported today is with the glue technology. And the models are solver validated, meaning that it will not let you run unless the model is checked against the solver capabilities and the functionalities. And it also comes with the integrated and interactive, easy to use post-processor. These are, in a nutshell, the technology, the underlying, the structures product line in Cheetah. And the continued enhancements on the modelers includes that the auto extend capabilities that works with the general bodies, and we continue to improve the stitching robustness, and we also have consolidated the two different GUI that we had for the defeaturing into one, and we also include the what is called the checks and the fix of the geometry, and we take our kernel power to do the checks. When the model is imported, if there are any corruption data, and we automatically detect that one, we also give you some kind of visual tool to find what are the errors in the model possibly be upon importing, and we also give you the auto fix. And most of these things will help you, the downstream operations like the direct modeling, edge and vertex drag, etc., the model become clean. And we do also have what is called automatic mesh quality enhancement that is included in this release. So let's talk about what is the computational parts based system. All of you are familiar with the traditional process that starts with the CAD model bringing into any system, and we go ahead and build the mesh model, we assemble the model, and we export the solver decks coming out of that model, and we run the simulation, and generally it would take about 2 to 10 iterations just to get the first run ready, which is the correctness of the model, not necessarily the iterations on the design, this is basically to make sure the run ready deck is created. After we do that one, and basically now we go through the design iterations, and every time that you make any change in any part of the system assembly, we have to go through reassembling the model, rerun the entire assembly, and it takes quite a bit of time. This is today's traditional process. But what we have in computational parts based system, this system is built on part based technology. For every part in the assembly that we bring into MSC Apex, first thing what we do is to create the computational parts, meaning we convert that part into a math model that represents the mass matrix, stiffness matrix, and wherever necessary, even the damping matrices. And once we create those math models, we assemble those math models. We run that math model, and this assembly could have multiple assemblies and nested sub-assemblies, or even a single part, whatever the case may be. And then once we assemble the model, we run that simulation, we review the results. At this point in time, the most important thing is how do we use the system for trade-off studies? Meaning, in your biggest assembly, whatever the case may be, if you would like to make any design change for a single part or even a single nested assembly, then only that part is going to be regenerated. And wherever that part interacts with the rest of the model, rest of the assembly parts, only those parts gets updated, and anything that is generative that needs to be updated, it automatically regenerates those things and assembles the model and reruns the simulation. So by looking at this one, if you can read between the lines, the computational parts-based system will allow you to run the simulation at an assembly level, and you can do the trade-off studies at any part level in a fraction of a time, because we reuse all the computational parts that was created to begin with, and we don't need to reassemble the models that are not affected. Meaning, in the system, we generate, we assemble, we solve, and we recover the results. And today in MSC Apex Cheetah, the parts are assembled together once it is meshed by what is called the glue. And in order to create the glue, there are two tolerances that we use. One is what is called the pair tolerance. This is to find the parts in the assembly that they are likely to touch each other within the tolerance that was given. And once we find the pairs in that assembly model, the next thing is to find the elements that are touching each other, or it could be the faces of the tetra elements or even the hexa elements or the solid elements. We are going to find those group of elements by what is called the either auto search tolerance, or manually you can give an input within which it is going to find all those segments that's going to be coming into play in the context. The glue patch tolerance we find based on the minimum gap between the parts within each pairs, and we use like a 10% of the average element edge length to find all the elements that's going to be in contact, and those things are going to be permanently glued. So here is a laundry list of things that you will have in our structures product as well as the modular product, and you are going to see many of these things in the two demos that you are going to see in the coming minutes. And let's go to the demonstration. The first demonstration is the structures part of the demonstration, and in this one we would like to demonstrate the computational parts based simulation and what is the generative behavior we talk about. For this, we are going to import a CAD assembly model, and we mesh the model, and we attribute the model with the properties and the material. We apply the loads and the constraints. Then we create the glue interaction between the parts in that assembly. Then we create a scenario. That means we assemble the model to set for simulation and run the simulation and interact with the post-process order. This is kind of an run-of-the-mill baseline analysis starting from importing the data. And now, in order to communicate the generative behavior in nature, what we would like to do in this assembly, we're going to modify one of the design. One of the part, we are going to modify the design. Then we are going to increase the thickness of some parts. Then we are also going to modify the loads distribution, and we are also going to kind of update the constraints region, and then rerun the simulation. And how all these things are going to be generative in nature, you are going to see in the demonstration. And we can switch the scenarios from static to modal analysis, rerun that one. All these things are going to be part of the first part of the demo. Now let's go to the demonstration. Okay, here is our MSC Apex Cheetah user interface, and it's pretty much that what you have seen. in the previous two releases. Let's start with importing the geometry. Import the model is the model that I'm importing is 1/4 of one of the automotive subsystems, which is a subframe in this case, and it has about 11 parts at this point in time. And we are going to go and mesh this assembly of parts. Let's start with, let's say, 4 mm mesh size, and mesh all the parts. The next step is to create a material and assign to all these parts. I'm going to create the classic steel material. Sorry. Then assign this material, in this case, to all the parts. Then we are going to create the section and create a section. And at this point in time, I'm going to create one section with the 3 mm thickness and assign to all the parts in this assembly. Then define the section behavior, and let's go with the default behavior and assign that behavior to all the parts. So now, just pretty much we meshed the model, attributed the model. Let's go ahead and create the loads and the constraints. And let's create the fixed constraints, and let's apply the constraints on the geometry instead of applying on the FE entities. I'm going to select these edges of this cut plane along with I'm constraining this model. This is the second cut plane, and this is the third cut plane. And I would have created some kind of symmetry boundary condition to begin with to represent the rest of the model. But with the interest of time, I just went ahead and created the constraints, fixed constraint rather. The next thing is to apply the forces. And let's apply the forces along this bushing area. In this case, I'm going to apply 1000 newtons in negative z direction, and I'm going to apply at about 4 of these locations along the periphery of this bushing area. Okay. So loads and the constraints are done. And the next step in this assembly is to create a glue interaction between the parts. And here is the tool to create the glue and create glue. And if you notice, we have all these parts have a 3 mm thickness, and all these parts are touching each other because in this assembly they're going to be welded in the real life. And the gap between these two parts is going to be approximately 3 mm because the thickness is 3 mm. Let's go ahead and use the default 5 mm to find the pairs, and going to go use the auto tolerance to find the glue patch. So I'm going to select the entire assembly to create the glue patch. Let's change it to kind of transparent mode so that we can see where the glue is created. And maybe change the thickness of transparency. So you can see those are all the glue patches between the parts that are assembled. Looks pretty decent. And close this one. Now the model is just about ready. We meshed the model, attributed the model, created the loads of the constraints, and we glue the parts together. And in the bottom area, what you see is new in Cheetah. This is what is called analysis readiness. Creating the model, checking the model, create an assembly representation of the model, running the simulation is as simple as clicking 1, 2, and 3. That's what you see right in the user interface as well. And in a given assembly, you can do this simulation either at a single part level or at a multiple parts level, or you can create a subassembly out of this one and move the parts into that subassembly, or you can analyze the entire assembly. And how do we do that one? And at this point in time, I'm going to go at the entire assembly level, set to analysis context. So now all these things get highlighted and it is ready for those 3 operations. And let's start with the static analysis of the system. And let me bring the mesh back, and maybe I can set the transparency back to normal. And I'm going to click on number 1, analysis readiness. At this point in time, it is pretty much checking the model to make sure that every entity in the model is ready for analysis, and it is checking against the integrated solver. And if you notice here, we found some issue. And when it highlighted with the red, that means the model is not ready to run the simulation. If it is yellow, it's only a warning, right? And when you look at the model browser, it tells me that part 4 has a problem, and it is also telling me it has some invalid elements quality which is preventing from the simulation. And let's go and take a look at that part 4, and I'm going to show only, and I'm going to check the element quality because that's what is being complained, and put the geometry off. Now in this, let's take a look at where are the invalid elements. I'm going to show only the invalid elements, and I go around this failed element a couple of times to see where is this element. You can see this is one of the elements which is so narrow and that is failing the quality criteria. And now we have multiple ways of fixing that one. Either you can do the auto enhance, or we can do the traditional way of fixing the elements, either by moving the nodes or splitting the elements or aligning the nodes, etc. In this case, I'm going to move this node, move node from this to that location, thereby and eliminating that particular failed element. Now I can go back to click on this button, number 1, to ensure that got corrected. Now if you see, the model is ready for the next step because it passed all the model criteria. Second one is to click on this button number 2, which is to create the assembly of the model that is going to be set to the simulation. This is like analogous to what you are all familiar with, creating the executive control, case control, and bulk data, and exporting the deck. None of those things are necessary in our system because everything is built in. And now under the studies tab, you see the assembly representation of that model, and this is the one what we created, and it has no errors, so-called information only, and this is the assembly that what it created by default, and it used the loads that was applied to the system and used all the constraints, and also create the default output requests that what it, as you can see here, it's going to give us displacements, applied loads, and the stresses, etc. And now it is ready to run the simulation. Going back to this setting, show all, and take a look at it once before we run the simulation. Now I'm going to run the simulation, which may take about a minute and a half to 2 minutes. And if you look at on the bottom left corner, it is going through those 4 processes, meaning generate, assemble, solve, and results, recovery of the results. For all the 11 parts in this assembly, the first step is it created the computational parts. Then it looked at where are the parts are touching each other, where the glues are created. And using all those information and all the computational parts are assembled. Then it looked at where the loads are applied, where the constraints are created. And you guys are familiar with the equation of motion that what we solve even in Astran, and it is the similar equations of motion that we are solving even in the integrated solver within MSC Apex. And right now it is solving those equations, and once it solves all those equations, then it will go and recover the results for all those 11 parts. And then once it is done, we are going to take a look at the post-processing functionalities, and then that is the baseline analysis. The second run, what we would like to do for the generative behavior is going to be, like I said, we can modify some designs in the assembly. We can make any kind of modification that one sought as a design intent, right? and I think it's coming to a recovery of the results. As soon as it is done, then we'll jump to the next step. And post-processing, like I said, it's an integrated, clicking on this one take you to the post-processing mode. Now let me do the display of the nodes. Okay, and quickly we can look at what we call the hotspots identified. If I click on this one, it will show me where in the model there are highest displacements, because it is set to displacement at this point in time. And even you can ask how many that you would like to display, whether 4 locations or 25 locations, whatever the case may be in the model, it will highlight all those things. And then you can click on this to do the animation and set the fringe upon that one. Now let me lock this one, and you can toggle between stresses to the displacements or applied loads, and it will also show you where the loads are applied and its magnitude. And I'll go back to the stresses, then I can toggle between the different components of the stresses, and it will update automatically as we click through each of these different variants, going back to the one with stresses. So it is as simple, as easy as that one to navigate through the post-processing. Now let's go to the what is called the design modification and the generative behavior. Okay, let's take a look at one of these parts in this assembly and make some changes to that only. Show only. I picked only one of the parts, which is highlighted here, showing that one is part number 6. Okay, and let's look at making some changes to this part. The first change, let's modify that whole diameter using the direct modeling tool, the edge and the vertex drag. I use that edge drag to change the whole dimension. And let's say I would like to do some other modifications, like splitting this face maybe from somewhere here to here. As you can notice, anytime I'm making the change, the underlying mesh is getting updated. At the same time, wherever the mesh interacts with the rest of the part also gets updated. Let's click and make some more changes from here to here. And basically, I'm making a part a little flexible and creating that hole. Okay, let's assume that along the edge, it is glued to the other parts, and just for the sake of showing the generative behavior and where the glue should be getting automatically updated, I'm going to remesh this part maybe from 4 mm to 5 mm and change that mesh. So this is a classic way that the end user would make the design changes, and we could use even the push-pull technology what we have as a direct modeling if the models happens to be the solid elements, right? Now let's go and display show all, and in this model let's make some changes to the thickness for some of the parts. Create a new section, and let's make a new section with 4 mm and assign that section to maybe this part. And wherever the part, when it's updated, wherever this part interacts with the other parts in the model, and all those glue automatically get generated. Now let's take a look at some other changes. For example, we apply the loads at these 4 different locations. Now let's say I would like to modify this load vector. I double click on that one, and interactively I should be able to modify the vector direction. You can also enter the values in these fields and also modify the magnitude. And that's one through graphical interaction. The next one, maybe if I would like to modify this to a given vector direction, for example, I'm making it as 45 degrees to the global XYZ, and now I apply that one. Now you see these 45 degrees to the changes. And also likewise, you should be able to change maybe the magnitude. Okay, so we did quite a bit of changes in the modifications to the forces vectors, and since we noticed this is the area where we were seeing the high stresses, and I kind of thinking that I may remesh this area locally so that the things gets updated, right? And surface mesh, let's make that local mesh refinement with 3 millimeter, and I would like to select only some faces of that sheet body, and I select only those. As you can see, the mesh got updated with 3 millimeter. So in this one, we did quite a bit of changes. Number one, we modified the design of another part. Number two, we increased the thickness of this part, and we modified the area mesh here, and we also changed the orientation of the vectors. Now, if there were any things that violate the mesh condition or the assembly condition, we would have seen the red mark here saying that some things are broken in the model. And now, since everything seems to be intact and it's solver validated, we can click this button to rerun the simulation with all these changes. Okay, so now what it is doing, only the parts that got affected with the changes that what we did is getting updated. For example, sorry about that. For example, this part we modified, it is regenerating the computational part. And we change the thickness for this one, it is going to update the computational part. And this part is touching, in this case, almost 1, 2, 3, 4, 5 different parts. That means all the glue is going to be updated. And we change the thickness here. Because of that one, all the glue that is connected to this part is going to be updated. And here, since we remeshed that one, and this the constraint, that is what is applied on the geometry, is going to be recreated and updated. So we made quite a bit of changes here, and probably if I were to make the change only to one of the part that is kind of isolated in this entire assembly, then we should have seen how the computational part, generative behavior, incremental solver would have been much better. In this case, probably it takes about a minute instead of 2 minutes for the baseline, and we got the results, right? And now I can click on post-processor and take you back to the post-processor mode, and now I can take a look at the same hotspots. Before it was about 1.6 millimeter, as you can see now it become 1.3. And just to let you know that the system, how it updates and how it reruns and showing you the behavior, right? And this is the design changes and the static analysis what we did. And the next thing is, what I would like to do here, I'm going to go back to the model, and at the assembly level, I'm going to set it to the analysis context and change this one to the normal modes. And now rerun the simulation. It's as easy as that one to switch from the linear static analysis to the normal modes analysis of that assembly. Now at this point in time, it is going to reuse all those computational parts that were created previously and assemble the parts together. And in this case, since it's going to be modal analysis, it's going to extract the eigenvector for the entire assembly. And this time it's going to take about 40 or 45 seconds to regenerate those model results, and it should be ready in just about 10-15 seconds. And like I repeat, in the computational parts based system, what we do is to create computational parts, assemble, solve, and recover the results. And right now we recover the results for modal analysis. Now I go back to the modes navigator, which is yet another easy to use tool to navigate the modes. And let's say I would like to start from one of first mode, and it's showing the animation. And let me lock this panel. And here is another useful tool that I can change the contours, how I would like to look at the mode shapes and the mode vectors, right? Now once I set that one, then I can lock to this. After that, now if I navigate to the second mode, it is showing the modal behavior and eigenvector with respect to the locked condition. That means you should be able to identify in which area the eigenvectors are more dominant or more participating, or whatever the case may be. I think it is left to your imagination how you would like to slice and dice the results interpretations. And likewise, if you were to do the two linear static analysis, and if you lock the baseline analysis contour with respect to that one, you can plot the second time around so that you can compare the two different runs, right? And it is as easy as that, as simple as that one. And you can see how user experience be very user friendly, easy to use, and it's fun to use. And this is the first computational parts based system, and we show you how to set up the model, how to run the simulation, how to rerun the simulation for the incremental solve, and what we mean by generative behavior, how we can switch the analysis context from one to another one and rerun the model, etc., etc. That completes the first analysis, or the first demo rather. Now let me go back to my PowerPoint to set the expectation what we are going to see in the second part of the demo. The second part of the demo, or rather the second demo, is to build a system with an orphan mesh, meaning we can import the mesh into the system and also import the CAD geometry and then combine the two together and then run the simulation. In the demo sequence, we are going to import one half of the BDF model, and then we review the units coming in and import the other half of the CAD model and translate, rotate, and orient and align that model with respect to the first half. That's how it looks. And we can take a look at the new GUI for the defeaturing to delete some holes or whatever the case may be. And extract midplane for all the geometry, the new part of the geometry that we import. Then auto extend of all faces and do some edge and vertex drag on the general body. And mesh the model, attribute the model, and create a glue between the two halves of the model, and check the solver validation and run readiness and run the simulation. And we are not going to run the simulation because it's going to take about 20 minutes for this big model, but we do the rest of the parts as a part of the demo to show you all the new capabilities in the modeler side, and also how we can take advantage of bringing the orphan mesh and assemble that one with the rest of the model. With that, I go back to Apex and file, close this. All right. I'm going to import the BDF, and I'm going to browse the model to identify where I'm loading in and preview that one before we import to the database. So here it gives you the statistics of the model, all the contents, what is there in the model, and what we have supported in this release, and which are those entities that are going to get populated into the database. And here is the setting of the units, and this model coming in as millimeters. I'm going to set to that one. And you can organize the model in Apex in multiple ways. Either we can organize the model based on material, based on properties, and based on contiguous region, etc., etc. At this point in time, it identified there are about 19 properties in this model, and hence it's going to create 19 parts. And remember that Apex Cheetah, or rather Apex is a parts-based system. We convert everything into the parts. So we are importing that BDF. And as you can see on the model browser, it created 19 different parts. Okay. And now let's create an assembly and move all those parts into that assembly. Create an assembly, select all the parts, and move to this assembly. Okay, now let's bring in the other half of the model, which is CAD. Import geometry. Import. Okay, so you see here, one half is imported PDF, other half is the original CAD model. And that consists of almost 63 different parts in the model. And originally somebody built this other half, they did not consider some of the parts, and maybe we can do the same thing here too. And let me put off this PDF from the display and set it to some view. Just a minute. And I'm going to delete some of the parts which is also not meshed in the original PDF. That, and also I think this part is not considered in the original PDF. Okay, and we can set a unique color for each of the parts based on the bodies or the parts. Here is, and this is one CAD part, one assembly that we imported consists of so many bodies. Now here is a new UI for D feature, and these are the two that what we had before as a two separate UI. Now we consolidated into one, and this is the manual user interface through which you can pretty much use any of these options. Let's say I would like to select this one. When you click on that, it automatically detects that feature and deletes the feature. Likewise, you can select a face or select an edge, whatever the case may be, to defeature that. And let's go back to the other tool and identify all the small holes in the model and delete all those small holes. That's not necessary from the meshing point of view. And let me set it to maybe 50 millimeter. And there are some small holes in this model which is too small for analysis intent. So deleted all the holes less than 25 millimeter. Looks clean. Okay. And the next step is to extract the midplane geometry for all these 3D solid bodies. And as you can see in this one, most of these parts are all constant thickness. I'm going to use that option to create the midplane for all these parts. And for 63 parts, it did create midplane. Now I can put this midplane geometry off, and you can see these are all the solids, and these are the sheet bodies. And even we can set a unique color for each of the sheet body that it created from the solids. Now, for the convenience, I'm just going to select all these solid bodies and delete them. Now you see here, these are all the sheet bodies. Now we would like to use what is the auto extend to extend all these parts and create one congruent geometry. Auto extend, and I'm going to use about 20 millimeter auto extend each bodies, and maybe about 4 millimeter as a tolerance to clear up all those extra sliver surfaces, whatever it creates upon auto extend. Now I'm going to select all the parts on auto extend. So as you can watch in the model browser, now all these sheet bodies are getting auto extended, and it left with one general body, and there is one part or one surface that did not get extended. Let's take a look at why and what's the issue with that. Okay, let's change the color of this part. Okay, and here is a part that did not get extended. As you can see, this is doubly curved part that was trying to extend from both the direction, and probably that failed for the auto extend. But no worries, how do we fix that one? I could use just auto extend this part randomly beyond some dimension, and now I can extend this part using the favorite edge and vertex drag tool to extend and create congruency between those two. That and this edge. Oops. Okay, done. Now you see there is only one general body. That means it is congruent between all those sheet body that we created. And now let's go ahead and delete that extra piece that we kind of extended beyond just to get by what we wanted to do. Okay, so now it is ready for the next step, which is going to mesh this part. Before that, I think there are two small areas where I might need to do the edge and vertex drag. Otherwise, we will have two small sliver elements in this case. Oops, that may not be the right behavior, and I do it opposite, and looks pretty consistent and looks nice. Okay, then generally I would like to kind of suppress all the free vertices, otherwise we unnecessarily create some small elements, and set it to vertex and select all the vertices of the model and suppress those things. Okay, suppression is done. Now I'm going to use surface mesh, and most of the mesh in the other part of the half of the model is generally about 10 millimeter. That's what I'm going to use to mesh this part. 10. All right, it's just about finishing meshing this one big part, and it created about 300,000 elements in the half, and the other half has another 300,000. So we are talking about 500,000 elements, maybe about 25 million degrees of freedom model in this case. And here we know that there are some bigger parts in the model that we don't need to have that refined elements. I can interactively go and select that face and mesh that one with 20 millimeter. So it's going to regenerate that one and makes the transition and update the mesh, and everything looks pretty nice. Now this is just about ready to assemble with the other part of the model. Before that, I would like to just take a quick look at the quality of the model mesh to see that it is solver validated or if there are any issues. So looks everything green, and let's say if I hide, and I can hide all the good elements, or I can keep only the invalid elements. Now I can grow to find if there are any bad elements. So interestingly, there are no invalid elements in that particular meshed part. Okay, so before we assemble with the rest of the other half of the assembly, I'm going to attribute this one. I'm going to use one of the material that's already available in the database, assign that material, and create a section, or I can use one of the sections also assemble in this model and use that one. And likewise, the associated behavior I'm going to attribute. So pretty much now this half of the model is just about ready with all the attribution. Okay, now this is the assembly of the original half, and now I'm going to drag this new part that we created into that assembly. Now we have all of these parts together and everything is disconnected. The last step in this one is to go through glue creation, create glue, and this model is pretty like a 2 meter size, and I'm going to give about 20 millimeter to find all this glue paste, and I'll continue to use auto tolerance for the glue patch. I'm going to select all the parts in the model. And now there are a couple of things that we can notice here. When we imported the PDF, we had 19 parts. And even though all those 19 parts were congruently meshed, but when we brought into Apex, we created the discrete parts for each of them. That means at every location where they were connected to each other, we created the additional nodes and with zero gap. That is the half of the model. And the other half, we have created only one part just to show the capabilities of auto extend and general bodies and etc. Now other half of the model is still only one part. And from the end user point of view, there are a couple of things that one would do. I would have liked to equivalence all those half the model that we brought it in, so that it is still as 19 parts, but each of them are congruently equivalenced. And another half, instead of creating one part, I could have kept the solid bodies as is, and I could have extracted the thickness from all those solid bodies into that one sheet body that we created. So there are multiple ways that one can slice and dice depending on the analysis intent, but in this case I choose this option to show the capabilities that what we have in MSC Apex. Okay, so the glue creation is done. Let's take a look at what it did. Show only, and if you notice here, all those 19 parts that what we imported, and between those 19 parts it created the glue, and that's what you are seeing here. And along the midplane geometry, you can see the mesh is kind of discontinuous, but they're all glued together, right? And everything looks pretty nice at this point in time. And even here you can see this is the glue between the two parts on the imported PDF, and this midplane along which it created the glue connecting the two halves. Okay, and just to complete the storyboard, I'm going to create analysis context, and normal modes is okay. And now I'm going to click on this to see whether there are any issues in the model. All right, when we check the model against the solver, integrated solver, it did find some issue highlighting with the red here as well as here. And now if I scroll down here, at each part level, I don't see anything. And at this, here it's showing there is an empty glue patch. So let me go back to the glue and expand all the things. And let me scroll down. As you can see here, one of the glue patch is broken. That implies that it did create a pair with a given tolerance, but it did not create a patch. Let's look at only that one, and that is the area. And now let's see, show all, and maybe highlight this one. If you notice here, the blue part is to be connected to this kind of red one based on the pair, but certainly there is a bigger gap there and it did not find a patch, and therefore that became an empty glue, and therefore it is not ready to run. So what is the option we have? Once I identified the issue behind that one, I'm going to delete that one. And now if you see here, I can click on this solver validation to make sure now the model should be ready for further. And as you can see now, everything is yellow, means there is only information, there are no issues with the model. And creating the assembly representation. Now this is just about ready to run the simulation. I'm going to switch back to my PowerPoint where I have ran the simulation and basically captured the different modes, etc., running this model. And of course, this took about 20 minutes to run. And after the baseline analysis, so the next thing is to see that can I increase the thickness of these tubes, which is vibrating too much, or whatever the case may be. I think you guys are the best judge to make the decision like what design changes one would like to do and how do you use that one with a generative behavior to run the simulation with the computational parts based technology. Okay, so some housekeeping. So along with the release, you have the release guide, and we recommend that you go through this one before you start using the product so that you will have an understanding of what's new and a brief description for what's new. And also we would like to get feedback through what is called IRT, we're going to see in a minute. And it also comes with known limitations and the known defects in the release guide. And IRT is an integrated reporting tool, which is an integrated tool in the product, which makes it a lot convenient for you guys to send us the feedback. It could be any enhancement request, and even if you find some workarounds, and you can tell us so that we can share that information with the rest of the user community. And please make sure that you give your email address here so that upon receiving any feedback from you, you get the feedback from us once you give your email. So with that, we certainly recommend why you should use Cheetah. So you know the Cheetah's the best qualities are it uses its non-retractable claws for its prey. It has a very flexible backbone. It is a long tail which it uses to navigate its direction, and it is a long nostrils and the lungs which holds enough oxygen so that it can run fast and much better. And analogous to that one, what are the benefits that we have in MSC Apex Cheetah for which that you will like, which is the integrated solver and the post-processor that is a traction. And as you saw through the demos, which is generative behavior and glue technology, it is flexible. And analysis readiness and solver validated modeling that guides through the user so that anytime that we do, whether it is a meshing or whether it's an assembly, it is solver validated and it runs through the simulation. It helps and it guides you set up the models. And computational parts based system helps you to do the system level simulation, yet you can also do the incremental solution power behind the MSC Apex Cheetah. Having said that, we let the Cheetah out and you be the judge. Hope you will have the best user experience taking advantage of what you saw. With that, sorry about that. Thanking you for your attention, and that's my presentation. Now leave it for the questions.